Hey, welcome neighbors. Today I'm making this video to help a neighbor. A while back my neighbor came to me and says, hey, is there a way to actually check the ABS sensor signal without using a scan tool or one with the bidirectional data or live data readings on it? Could you check it with a multimeter? And at that point, I didn't really have an answer for him because at that point, I didn't really know what kind of signals that the ABS sensor sends. Well, after doing a bit of research, I decided to make this video because I believe I can make a simple device for anybody to check if their ABS sensor is working correctly, and the tone wheel, of course. So to give you an idea of why I think we can make a device that will check the ABS sensor, is to tell you a little bit about how the ABS sensor works and the signals that it produces. So basically, on your hubs, this is the hub, the circle. This is what it's called a tone ring. So here, there's many teeth. I believe, no, when I did some Googling around, there are about 44 teeth around your tone ring. And then it goes around like this, and it's like so, right? And usually your ABS sensor is mounted adjacent to this tone wheel. So there's going to be a sensor coming down like this in here, right? Which has a magnetic or inductive pickup, which basically, as this wheel turns around, as this sensor passes by these teeth, right, as this thing spins and this passes by the teeth, it will generate a signal along these two wires like this, right? This one goes to the ABS sensor connector, right, over here. Now you may be wondering, how does a two-wire system like this even work? Well, the kind of signal it outputs is a alternating current, okay, like this. But its frequency is directly related to how quickly the little teeth pass by this sensor. So if it takes 1 second, let's say there are 40 teeth on this. If it takes 1 second for this wheel to completely come around, then it's going to be passing the teeth 40 times, right? It passes 40 times, so it's going to make 40 peaks here, okay? So if that took 1 second, we will call that a 40 hertz signal. Okay, so that is the frequency. Now the frequency, as I mentioned, it just depends on how many times it changes, right? And herein lies why it's difficult to measure this signal. Number one, this signal is an alternating current. So if you were to take a multimeter here and hook it up to one of the wires, and because it is a alternating current signal, it doesn't matter which, there's no polarity involved in it, right? So what you would see on here, you would try to read an alternating current. But the issue is that on standard multimeters, this is designed to read 60 hertz signals, right? And if you don't have a multimeter that can read different frequencies, then this is going to be troublesome. It may not work for you. The second thing that's hard is that the amplitude of the signal, right, is very small. We're talking about peak to peak, about what I've read is about 0.5 volts. Okay, so it can be a very small signal. And I also believe that this signal is related to the RPM, okay, of this wheel. So the slower it is, the signal may be actually smaller peak to peak than 0.5 volts, and the multimeter will not read it. Yes, an oscilloscope will read it, but most of us don't got an oscilloscope. I have one. for my electronics work, but my neighbor doesn't have one. So, and many of you may not have one. So let me try to get into that and into how we can do this. Now, the reason why I believe we can do this is because this type of signal is very similar to another type of signal that is very commonly processed and very commonly measured. And this is, if anybody, if any of you the viewers here know about audio equipment and radio, you know that this signal is very similar to, well, it's very similar to AM or FM radio, right? All we got to do here, basically what we need to do is amplify this signal and then have some kind of an indicator knowing to show what the signal level is at. So basically, you can think of it like this. We will feed the signal, right? So this is, if this is the sensor here, we will feed this signal into a, first of all, an amplifier, right? So I don't remember the signal, the symbol for the amplifier, but we feed it to the amplifier, and the amplifier will feed it to a, you can feed it to a speaker, right? Or in this case, the way I think we should do it is, because I'm much better at visual cue than to listen to things. My ears are not that sensitive, although you can probably create the same device using a headset. You could potentially hear the signals and how even they are or not. My preference is I like a visual cue, so I'm gonna make a device that's gonna be based on visual cue. I'm gonna try to light up an LED every time we hit the peak on the signal. All right. So the way this tool will work, hopefully, is that you disconnect your ABS sensor, right, and plug in you have some probes. The tool will have a probe. Will plug into the ABS plug, and what you will do is spin the wheel over, okay? And as you spin the wheel over, the tool should give you a visual indication of each time we pass the tooth, okay? And this signal, since it is quite small, it's not that small in terms of radio, right? Radio is probably a lot smaller than these signals. But we're going to be able to amplify this signal to be able to show a visual cue, which in this case would be an LED. So let's get into the circuit design. So here we go. This is the basic circuit. Now let's just go over at a logical level how this works. All right. So we have a power supply VCC. We have our ground here to our system. So more likely than not, we're going to power this with some batteries, and this is a very simple system here. So your sensor is going to be plugged into one of the terminals of the device will be plugging into the sensor here, right? So one of the wires of the sensors, and the other wire of the sensor will go to the ground of the device, as shown here. So how this works is that we're going to try to see the capacitor here. This is a symbol for capacitor. We're going to be trying to read the signal into the base of this transistor here. This is an NPN transistor, okay? NPN, okay? And what this is going to do, the transistor is going to amplify that signal, because as I mentioned before, this sensor signal is very small. There's no way you can directly power a microphone or even a small LED to even make any kind of visual indication. It's just too small, the signal. So this transistor's job is to amplify that signal. How is it going to amplify it? Well, transistors have a gain, and this in this setup, this is called the common emitter setup. We're gonna pick up, the output is picked up on this line here. And so what this is going to do is this is going to amplify that voltage. So before, the peak to peak was about 0.25 volts, right? Sorry, 5 volts. And if you look at the positive and negative part of the cycle of the signal, it's only at max is going to be only half of that, right? Half above ground and half below the zero. So what it's going to do, this transistor will amplify the voltage signal, hopefully enough to be able to, basically, the reason why we have two transistors here is because this will basically amplify the signal big enough such that it becomes a logic level signal. So something that's perhaps about 3 volts, 3 to 5 volts, something like that, okay? Some signal that is clearly indicating an on or off signal, okay? So when we look at the wave that comes in, we want these peaks to be on signals. We want anything below that to be off signals, right? Off down here and on up here. So we want to make that perfectly clear in this system. So we amplify it here, and the amplified output goes to another transistor, which yet amplifies again enough to light up this LED. So only when we're on the logic on level, okay, when we're high, that this light will turn on, right? And the current will flow through this from the power source, the VCC will come through this resistor, through the LED, light it up, and the current will follow through the transistor and back to ground. So that's logically how we're going to do this. However, the secret is in how do we tune and how do we bias these transistors? How do we select the values of these resistors, right? And these transistors to actually get this to work. Now, and this capacitor, by the way. So we do have to know a little bit about the sensor signal and the strength, but we're going to make some assumptions here. We're only going to make an assumption that the greatest amount of the peak-to-peak voltage is 0.5 volts. That's all we're going to assume. So we're going to build this circuit, but first we've got to figure out all the resistance values, the capacitance values, and so in order to solve for all the resistance values, all these resistor values on this circuit, what we need to do is we need to find out what is the currents flowing through each of these points, the collector, emitter, and the base, right? The current determines all the values of this resistor. For a transistor in this configuration called the common emitter, we have to solve for, firstly, we have to solve for the current going through the collector first. And we have to also solve it for a certain point, okay? We have to solve it for when the signal is at 0. So basically, whenever we have a signal like this coming in through the sensor wire, we have to essentially solve it for the 0 point, the midpoint of this one, okay? So when it's 0 volts on this line. So it can be, remember, the peak can be 0.25 volts, and the trough at the bottom could be negative 0.25 volts, giving a total swing of 0.5 volts, right? But we need to solve this. We need to solve these currents for when the circuit is essentially at rest, when the signal is essentially at rest, okay? What that does is making sure that as soon as the signal either rises a little or drops a little, the transistor will react. It will give the largest linear reaction possible. That's why we have to center it to 0, and that's why we have to set the currents flowing through this through the base such that the transistor is basically ready to go. And that point, they call it the Q point on the transistor. So before I solve it, let's just take a step back for a moment. If you're new to electronics, essentially the function of a transistor in this configuration is to take the small amount of base current and multiply and amplify it on the collector. All right. So what it means is that a very, very small current change fluctuation in the base will result in a big change in the collector current. Now the output of this transistor in this configuration is considered right here. It is put right here. If you tap into this point, this is considered the output. Okay. So let's first solve the collector current. Okay. In order to solve for this, we need this. Here's some simple math. So we need to solve for IC, the current of the collector at the Q point of the transistor. So what we want to do here is one very simple equation here. IC equals to VCC minus VE divided by 2 divided by load resistance. So before we plug in the values here, we're going to talk a little bit about what this means. So VCC is the operating voltage of the battery of our device. That's the total amount of voltage that we have to use. VE, let's go back to the diagram, is the voltage at the resistor called RE here. That's below the emitter of the transistor. We need to find out what the voltage is dropping here. Okay. When it's at the Q point, okay, divided by the load resistance. So that's the load, and RL is the load resistance. Okay. So I'm going to explain a little bit about this equation. Now, if you look at this, this is actually a very simple equation. This is just Ohm's law. Okay. So the top part, as you can see, if you break it down, this just produces a voltage and divided by the resistance. Now, voltage divided by resistance is the current that's becomes the current that is moving through that unit. Okay, so this is where that equation comes from. But what we have to try to understand, which I explain, is a little bit about how to find this Q point, right? Why is it this? Why is it VCC minus VE over 2, right? What's this? What's the story behind this? Okay, I'm going to show you that in a minute. So I've redrawn this diagram, the transistor, just to illustrate what's going on here. What is the Q point we're trying to find, and why VCC over minus VE divided by 2? What is in that? So basically, what we're trying to do is find the collector's this current when this transistor is in a state that's half open, half closed. You can think of it in that way, in terms of voltages. Okay, so you can imagine now. The first thing, the easiest thing to explain, to get rid of, is minus VE. Okay. Where does that come from? Because this part, if you measured the voltage here with a probe, this would be VE. That's the voltage between the emitter and ground. Okay, that is known as VE. So we're not really too concerned about that at the moment. That's why we're kind of eliminating it from the picture. But you have to realize that now we're dealing with only this part of the circuit. So in other words, in solving this, if we know what the current is flowing through a transistor, we also know the current current going through a resistor, and vice versa, right? So let's take a look at this. right? Because we're actually talking about the transistor. It's the transistor that provides the function of letting current go through and or not, right? So we're only talking about the properties of that transistor. So let's put it this way. I'll draw another diagram to show the voltages when the transistor is fully closed, and I'll show another diagram when the transistor is fully open. So I've redrawn this diagram so that the transistor is in both states. This is when the transistor is off, and this is when the transistor is on. So what we're trying to do is find the voltage of the transistor when it's halfway between on and off. Okay, so on the off state, this is easier to understand. The transistor is fully off, and so if we measured the voltage at VC, the voltage at the collector, VC will essentially equal VCC. Because there's no current, no voltage drop through resistor. Okay? Now, when we look at the transistor fully on state, because it's fully connected, if you had measured the voltage at the collector, then you will notice that the voltage is actually the same voltage as the emitter, right? Because now this is essentially a joined wire. If you measured it, it would just be the voltage at the emitter, okay? Because the voltage has been dropped through resistor RL here, at the load resistor. So I hope this becomes an eureka moment, because VCC minus VE, it's the difference between this level on the off state and the on state. VCC minus E. That gives you the range of the voltage, and in that range, we'll divide it by 2. That's how we find the midpoint. So back to solving for I with actual numbers. So here I took VCC as 4 volts minus VE as 0.25 volts, all over 2 divided by resistance of L. Now, I believe we talked briefly about the 0.5 volts, which is the VE. Now, going back to this, just a reminder why we have a VE of 0.25. That's because right at this point, we need to keep it at, when it's the midpoint of the transistor, the signal can swing either way. It can swing up and swing down. I'm believing that the sensor, when it generates the signal into the base, the swing is plus 0.25 and minus 0.25. So when the signal comes in, it's naturally going to want to push it's going to not push, well, basically because the current will be reduced on the lower half of the cycle, the base current reduces, and therefore the current through the collector reduces, and therefore the voltage dropped across the current passing through RE will be reduced, and therefore the voltage drop will be reduced. So I just don't want the voltage of this RE to drop below 0. That's why I wanted to keep at the midpoint. I wanted to keep the voltage of the emitter at 0.25 volts. So that's why that one was chosen. Now back to this one. Now, resistance of the load. Now I've chosen it at 1,000 for a couple of reasons. And to explain that one, we have to take another detour. To choose a value for the resistance load here, it's important to choose a value for both when the transistor is on, and also for when it is in an off state, because it will swing between an on and off state, right? Now, when the transistor here is off, anytime it's off, basically all of the current from the VCC will be flowing through the resistor here and flowing through this resistor that's leading into this transistor. Okay, so this will essentially form the base current for this transistor, and it will again, as a transistor, it will amplify that current going through the collector and through its emitter. So basically, when there's low or no current flowing through here this way, because this transistor is on, it'll be pulling all the current down here. Then there will be no current through here, and therefore the LED will be off, right? But as soon as the wave here closes, or basically opens the switch and fully disconnects, there will be no current traveling through through this path, through this transistor, and therefore all of the available current flowing from VCC through this will flow through the resistor RL and this RLX through to this transistor, causing the LED to be on. In order for that to happen though, so in order for that to work properly, the right amount of current must be flowing through to the transistor's base. So I've redrawn that diagram, only showing this part of the circuit with the LED. So most LEDs are like small hobby LEDs, have a 20 milliamp requirement for the current to flow through. That's when they're at their brightest and they're at their safest level without blowing. So in order to get 20 milliamp to flow through this circuit from the power supply, the collector must be the transistor must be open enough that the collector will flow that current through. And all transistors have a gain, which means the ratio between what is flowing through the base versus the collector. And basically what happens is a small signal, a small current on the base can trigger a large current flow through the collector. And usually if the transistor is operated in its optimal region, then this particular transistor, let's assume that it's has 100 times gain. So usually in transistor speak, they call it the beta. Okay, so the beta for this transistor we'll assume is equal to 100. So for every 1 milliamp that flows through the base, 100 times will flow through that collector. So therefore, if we do the math, if we need 20 milliamps, we must feed the base with 0.2 milliamps and just divide it by 100, right? So in order for that to happen, we have to choose resistors carefully such that the sum of RL and RLX must support the fact that it will drop, it will not only drop the amount of voltage that's required, but also only allow the 0.2 milliamps to flow through that. So let's solve this using Ohm's law again. Let's write down what we know, okay? So what we know is RL plus RLX, the combined resistances, right? And we know that we want 0.2 milliamperes to flow through them. So resistance times the current is equal to a voltage. Now, what voltage you say? The voltage is the voltage that's dropped between between this part of the circuit, all the resistors here, up to this point. That is characterized by VCC minus VBE. So VCC is the total circuit voltage minus VBE. VBE is the voltage drop between the base and the emitter. So if we take the total and we subtract this part out of it, then we get the voltage here, right? So that's what I've written here, this equation. So this VCC minus VBE equals to RL plus RLX times 0.2 milliamps. And this is just Ohm's law, right? Voltage equals resistance times current, right? So let's just do some rearranging and plugging in of values. Now, we know VCC 4 volts, right? 4 volts minus the 0.7 is 3.3. And then Basically, I've combined RL and RLX together as RTX. Just rewrite the symbol so that we can simplify this one a bit. Times the 0.2 milliamperes, right? Which gives, if RLX and RL was combined together as RTX, it would give 16.5k ohms. That's how much a combined resistor would need to be in order to support 0.2 milliamps flowing through it. Now, in reality, it's not one resistor. We got to split them up into two. So let's just find a ratio or just a general idea that makes it easy to to work with, right? So let's split RTX such that RL is 1000 ohms and RLX is 1550 500 ohms. So when you add them together, it's still 16500 ohms. It's just that now we split them up because the RL has a purpose. We're going to use that as part of the other circuit, transistor circuit here. All right. So finally, we're back from our detour. Now we know where we get these numbers from, and we're back to solving for the current through the collector at the Q point. Okay, so now we know where the 0.25 comes from. Now we know where the resistor load comes from, the 1000 ohms. So let's solve for that. 1.875 divided by 1000 ohms gives you collector current of 0.0018 amps. The base current will be 100 times less than this, so we divide by 100, 0.00018 amperes, okay? So this is set up by the type of transistor that you have, and the type of transistor we're going to use, or we're going to look for, is going to have a gain of 100 times. So whatever coming through the base, this amperage, it means 100 times the amperage will be going through the collector, right? So now I just went here and did a simple calculation, just a back check on my numbers to make sure that, you know, the type of components that we'll use will not burn out if too much amperage is being flowing through them. So simple check, right? We take the amperage through the collector and we multiply it by the voltage, right? And you get 0.0033 watts, which is essentially nothing. Most hobby resistors or any resistors you can find are at least a quarter watt, okay, which means 0.25 watts. So the amount of current flowing through this is essentially nothing. Don't worry about it. Now we got to solve for, finally, because we got all these currents going. Remember, said the whole reason why we're doing this is because we wanted to find out what these resistors are going to be, right? So now that we have the currents, we're ready to solve for the resistance values. So let's get into that. We're going to solve for R1, R2, and RE. Again here, we're going to solve for R2 using nothing more than Ohm's law, okay? So here, R2 is equal to this. The top part is a voltage, and the bottom is a current. So voltage divided by current is a resistance, right? So, and the reason why we arrange it this way is because VE, which remind you is this point here, plus voltage between BE becomes the voltage at R2, okay? If you can imagine, this is the voltage that's being dropped between the center point here and the R2. So that's equivalent to BE plus the voltage at E, okay? So going back to it, now, what is the current flowing through there? Well, this is the base current, okay, times 10. Now this is a general rule, okay? When you have this type of a setup of a voltage divider, we need to make sure that the current flowing through this entire circuit here from top to bottom, through R1 and R2, has to be 10 times, greater than the base current. Okay, this is because we want the voltage to be between here to be as stable as possible. Okay, and because the base current is very minimal compared to the current flowing through this circuit, it will not affect the voltage here. It will have a stable voltage, right, and not be affected by the base. So 10 times. So this reflects in our calculation. We said divide by 10 times the base current. Okay, so this will give us the resistance at R2. Okay, and which is VE is 0.25, as I've said before, plus 0.7 volts between the voltage between BE, divided by 0.00018 amps, right? That's the base current, multiplied by 10, that is, right? The answer to that is 5.277 ohms. Sorry, I didn't say 5.2. This is 5,277 ohms. Okay. Now, similarly, we're going to solve for R1. Okay. Now, what goes in R1? Because it's essentially, again, at R1, the current flowing through that, remember, it's all this is coming from VCC, coming down here. So logically, right, if 10 times the current of the base is flowing through R2, and 1 time of the base current is going down here, how much current has to be flowing down R1? Well, the answer is that, of course, 11 times the base current, right? Because if there's 11 times the base current here, 10 of those went down, 1 of them going this way. 10 plus 1, 11, right? So in order to solve for R1, it's divided by 11 times the base current. And what is it that we're solving on top here? What's this mess here? VCC minus, all in brackets, VE at the Q point plus BE. Well, that is basically saying that I'm taking VCC and I'm going to subtract out all of these components here. So we're only interested in the voltage drop between here. That's what we're saying, okay? We're taking the whole total circuit voltage, taking out the voltage drops in the junction here, and taking out the voltage drop here. Therefore, we got the voltage drop here, all right? So once again, if you substitute for the values, we get 4.0 volt minus 0.95 volts divided by 11 times of the base current, which is this 0.00198, equals, now I put the K here. This is actually roughly around 15K ohms, 15,000 ohms, okay? Now, let's solve for RE. Now, the RE is interesting because, again, remember we arbitrarily set VE as the voltage on the emitter as 0.25. Remember, the reasoning for that was we didn't want this to swing to 0, right? Or below 0 if the signal goes low, okay? Now, again, voltage over current. Now, the current, what's the current that we use that flows through the emitter resistor here? What is it? Well, it's the base current plus the collector current. As you see, these two are connected together. The current flows down and they join into this single path. Okay, so you got to add the collector current plus the base current. Now, usually, because the base current is so small, we don't really have to add these together. You just take the collector's current. The base current is always 100 times less, so it won't affect the numbers much. Okay, so, but anyways, here to be complete, I added them both together. So 0.25, base current plus collector current is 0.001818. So that gives us a division of 137 ohms. Okay, that's the resistance of RE. Now, just hang on a bit. It's just a bit more before we're done. So finally, we've got almost all of the resistances except for this one, RB. This one is the the resistor that drops the remaining voltage that's not dropped by the LED and the transistor. So let's solve that one. Actually, let's take another approach. We're just gonna take a best guess at it, right? This resistor isn't really all that important. All it really does, as I mentioned, is just drops the remaining voltage that's not dropped by the LED and the transistor. Now, I can't tell you exactly which LED I'm going to use. I'm guessing that this will drop at minimum maybe 1 volt to 2 volts, maybe 2.5 at the most. This transistor, at its state, I don't know how much voltage will be dropped between here either. So we take a best guess at it. We'll take our this is 20 milliamperes flowing through this entire circuit. So if we just choose a reasonably smallish kind of value for the resistor to flow this current through, let's just see how much voltage this will drop at 20 milliamps. So I'm just going to choose 100 ohms. So if it's 100 ohms flowing through here, what we're going to do is we can just see how much voltage drops, right? Voltage equal to current, right? To 20 milliamperes multiplied by 100 ohms. So that's easy math, right? So let's rewrite it, because milliamperes is like, it's actually amperes like this, 0.02 amps times 100, which will give us, just shift it, so 0.2 volts, right? So that's pretty good. If I'm only dropping 0.2 volts here, out of the 4 volts from VCC, if I drop 0.2 here and I don't know, 1 or 2 volts here and 1 or 2 volts here, probably, yeah, it'll probably do the job, right? I don't know until exactly I have these components. So I'd like to say congratulations if you made it this far into the video. We've talked about almost every component in this circuit diagram, and the only thing left to talk about is the capacitor. What capacitance value we need to use, polarized or non-polarized, and of course what the function of that capacitor does. So basically the capacitor here is the only thing it really does is blocks the DC voltage from backing into the sensor, which may damage it or may cause it not to generate the right signal. And also at the same time, it will let the AC wave come through, so it can be processed. And also it'll center the wave onto the bias voltage that we set for the transistor. So the voltage at this point will be the 0.25 plus the 0.7 volts between the junction here. So 0.95 volts here. The wave will be centered on this. So it will be at times it will be 0.25 volts above 0.95, and at times it will be below minus 0.25 below 0.95. So in the next video, we're going to actually build this circuit. Now I'm going to try to build this circuit for, let's say, less than $10 from using things that we can find in many stores and places. That will be a nice build. It will be a good video to watch. So stay tuned and subscribe if you want to see the next video. Thanks and have a nice day.